Cross product. Another vector operation under consideration is the cross product, denoted by symbol X or termit cross. Consider two vector A and B whose cross product we wish to evaluate. First, we write vector A cross vector B. Each individual component of vector A must be vector multiplied across each individual component of vector B. The first term is A sub x A hat sub x cross B sub x A hat sub x, leads to A sub x B sub x A hat sub x cross A hat sub x. This product possesses both a magnitude and a direction, as the cross product yields a vector quantity. Evaluating its magnitude first, magnitude of A hat sub x cross A hat sub x equals magnitude of A hat sub x times magnitude A hat sub x times sine 0. The magnitude of a unit vector is 1 and the angle between A hat sub x and itself is 0. Since sine 0 equals 0, the magnitude of this product equals 0. Thus, A hat sub x cross A hat sub x is 0. In general, the cross product of any unit vector with itself is 0. The second cross product term is A sub x A hat sub x cross B sub y A hat sub y. Multiplying the scalar magnitude yields A sub x B sub y, leaving the unit vector cross product A hat sub x cross A hat sub y. The magnitude of A hat sub x cross A hat sub y is given by magnitude of A hat sub x times magnitude of A hat sub y times sine theta equals 1 times sine 90 degrees equals to 1. To determine its direction, we apply the right-hand rule, pointing the index finger along the first vector direction, A hat sub x, and the middle finger along the second vector direction, A hat sub y. The extended thumb points in the direction of the resulting vector, which corresponds to positive A hat sub z. Thus, A hat sub x cross A hat sub y equals A hat sub z, completing the evolution of this term. The product of the first component with the third component is A sub x A hat sub x cross B sub z A hat sub z. The scalar magnitudes yield A sub x times B sub z, leaving A hat sub x cross A hat sub z. The magnitude of A hat sub x cross A hat sub z is 1 because the unit vectors are orthogonal. Applying the right-hand rule by aligning the index finger along A hat sub x and the middle finger along A hat sub z causes the thumb to point along minus A hat sub y. Therefore, A hat sub x cross A hat sub z equals minus A hat sub y, and this result obtained. We now proceed to the product of the second component with the first, A sub y A hat sub y cross B sub x A hat sub x. The scalar product is A sub y times B sub x. Since the cross product is anti-commutative, interchanging the vector order introduces a negative sign. So A hat sub y cross A hat sub x equals minus a hat sub x cross a hat sub y. Having previously established that a hat sub x cross a hat sub y equals a hat sub z, it follows that a hat sub y cross a hat sub x equals minus a hat z. Thus, this product evaluates to minus a sub y times b sub x a hat sub z. For the product of the second component with the second, since a unit vector is multiplied by itself, the vector cross product equals 0. Finally, we proceed to evaluate the second component multiplied by the third component. The term a sub y a hat sub y cross b sub z a hat sub z equals a sub y b sub z a hat sub y cross a hat sub z. The magnitude of a hat sub y cross a hat sub z equals 1. Determine its direction. Align the index finger of the right hand along the y-axis and the middle finger along the z-axis. The extending thumb points along the positive x-axis. Thus, the cross product evaluates to a sub y b sub z a hat sub x. For the product of the third component with the first a sub z a hat sub z cross b sub x a hat sub x equals a sub z b sub x times the quantity a hat sub z cross a hat sub x. Since a hat sub x cross a hat sub z equals negative a hat sub y, reversing the order gives a hat sub z cross a hat sub x equals negative quantity a hat sub x cross a hat sub z, which equals negative a hat sub y, which equals positive a hat sub y. Therefore, this term equals a sub z times b sub x a hat sub y. For the product of the third component with the second, a sub z a hat sub z cross b sub y a hat sub y equals a sub z b sub y a hat sub z cross a hat sub y. Since a hat sub y cross a hat sub z equals a hat sub x, reversing the vector order yields a hat sub z cross a hat sub y equals negative a hat sub x. Thus, this term evaluates to minus a sub z b sub y a hat sub x. Finally, the self-product of the third component a sub z a hat sub z cross b sub z a hat sub z equals 0. In summary, the 9 unit vector cross product are a hat sub x cross a hat sub x equals 0, a hat sub x cross a hat sub y equals a hat sub z, a hat sub x cross a hat sub z equals negative a hat sub y, a hat sub y cross a hat sub x equals negative a hat sub z, a hat sub y cross a hat sub y equals 0, a hat sub y cross a hat sub z equals a hat sub x, a hat sub z cross a hat sub x equals a hat sub y, a hat sub z cross a hat sub y equals negative a hat sub x, a hat sub z cross a hat sub z equals 0. To conceptualize these relationships easily, A right-hand cycle diagram can be utilized. Arranging a hat sub x, a hat sub y, and a hat sub z in a clockwise triangular orientation, navigating the direction of the arrows yielding positive result. A hat sub x cross a hat sub y result a hat sub z. A hat sub y cross a hat sub z equals a hat sub x, and a hat sub z cross a hat sub x equals a hat sub y. Whereas evaluating against the arrow direction introduces a negative sign, as a hat sub y cross a hat sub x equals negative a hat sub z. A hat sub x cross a hat sub z equals negative a hat sub y. Moving counterclockwise introduces a negative sign. This right-handed orientation for vector cross products simplifies evaluating the expansion of the first component of vector A across all three components of vector B. The first term is 0. The second term yields A sub x, B sub y, A hat sub z, since A hat sub x cross A hat sub y equals A hat sub z. The third term, directed counterclockwise, gives negative A sub x, B sub z, A hat sub y, as A hat sub x cross A hat sub z equals negative A hat sub y. Proceeding to the second and third components of vector A distributed across vector B, we utilize the same cyclic rule. Out of the 9 expanded terms, 3 evaluate to 0 and 6 remain non-zero. Grouping the non-zero terms pairwise by their unit vector directions yields A cross B equals open parentheses A sub y, B sub z minus A sub z, B sub y close parentheses A hat sub x plus open parentheses A sub z, B sub x minus A sub x, B sub z close parentheses A hat sub y plus open parentheses A sub x, B sub y minus A sub y, B sub x close parentheses A hat sub z. Equivalently, this cross product can be expressed as a 3 by 3 determinant in Cartesian coordinates. A cross B equals the determinant of the 3 by 3 matrix with row 1 A hat sub x, A hat sub y, A hat sub z, row 2 A sub x, A sub y, A sub z, row 3 B sub x, B sub y, B sub z. Expanding this determinant along the first row confirms the exact component formulation above. Example: find a unit vector perpendicular to vectors A and B. A equals A hat sub x plus A hat sub z, and B equals to A hat sub x plus A hat sub y plus A hat sub z. A vector orthogonal to both A and B is given by their cross product A cross B. To obtain a unit vector, we normalize this result by dividing by its magnitude and attaching a plus or minus sign to account for both perpendicular directions. So A hat sub n equals plus or minus the fraction a cross b over the magnitude of a cross b. Evaluating the cross product using the determinant setup. A cross b equals the determinant of row 1 a hat sub x, a hat sub y, a hat sub z, row 2 1 0 1, row 3 2 1 1. Expanding the determinant, a cross b equals, open parentheses, 0 times 1 minus 1 times 1, close parentheses, a hat sub x plus, open parentheses, 1 times 2 minus 1 times 1, close parentheses, a hat sub y plus, open parentheses, 1 times 1 minus 0 times 2, close parentheses, a hat sub z. Simplifying the result, a cross b equals negative a hat sub x plus a hat sub y plus a hat sub z. The magnitude of a cross b equals the square root of, open parentheses, negative 1, close parentheses, s squared plus 1s squared plus 1s squared, which equals the square root of 3. Substituting the magnitude into the normalization relationship yields a hat sub n equals plus or minus the fraction negative a hat sub x plus a hat sub y plus a hat sub z over the square root of 3. Example: for the given triangle formed by vectors a, b, and c satisfying vector addition a plus b equals c, prove the law of sines. Sine of a over the magnitude of vector a equals sine of b over the magnitude of vector b, which equals sine of c over the magnitude of vector c. To begin the proof, take the vector cross product of vector a with both sides of the vector addition equation, a cross, open parentheses, a plus b close parentheses equals a cross c. Applying the distributive property of the cross product gives a cross a plus a cross b equals a cross c. Since the self-cross product of any vector with itself is 0 due to an angle of 0 degrees, the equation simplifies to a cross b equals a cross c. Taking the magnitude of both sides, the magnitude of a cross b equals the magnitude of a cross c. Expressing the cross product magnitudes using the definition, magnitude of a cross b equals magnitude a magnitude b times sine theta. For magnitude a cross b, placing vectors a and b tail to tail shows that the angle between them is the supplementary angle pi minus c. For a cross c vectors a and c sharing a common origin from the interior angle b. Thus, magnitude of a times magnitude of b times sine of, open parentheses, pi minus c close parentheses equals magnitude of a times magnitude of c times sine of b. Dividing both sides by the non-zero magnitude of a and utilizing the trigonometry identity sine pi minus c equals sine c, regarding terms yield sine of b over magnitude of b equals sine of c over magnitude of c. Similarly, Taking the cross product of vector b with the original addition equation, a plus b equals c, establishes the second equality.